tell us about designing core selecting payment rules, computational search approach.
Hi, thank you. This is joint work with Benedikt Bünz and Sven Seuken. So this is the CA section, so I thought I would put the obligatory combinatorial auction slide up. We're interested in auctions with multiple goods and where bids are on packages of goods and where the values over those goods can exhibit both complements and substitutes. Here we're interested in a sealed bid version of this, such as what you would find in the supplementary phase of the CCA that we just saw. So by way of motivation, let's look at what VCG would do. VCG, of course, chooses the efficient allocation. So if a really simple example here where we have 3 bidders, where the efficient allocation is to give A1 to A to 1 and B to 2. And of course, that's what VCG will do. It will then charge the bidders the externality they impose, which in this case is 10 and 50, which we all know is going to be strategy proof. But the observation here is that the revenue adds up to less than what bidder 3 would be willing to pay. So here's 60 instead of 100. This is probably undesirable. And so the solution here is to implement core selecting rules instead of VCG because it improves revenue, but also because it avoids these ex post complaints about the implemented allocation and payments that are being charged. We can show this example pictorially in a picture like this, where the axes here are the bids being placed on each of the 2 items, item A and item B. Then we plot back on a graph like this the prices that are going to be charged or the payments that are going to be charged. And the payments that are in this blue region are what's called the core. And those prices in that region, for prices in that region, no coalition of bidders would be willing to outbid the winners. And then among those prices, we're going to be interested in the so-called minimum revenue core, which is to say those prices that are best for bidders. And as we just saw, it can often be the case that VCG is outside that set. So what do you do? Well, the quadratic rule is the one that has been implemented in practice. And what it does is it picks the point among all the ones in this set that is minimum by Euclidean distance to VCG. So it's going to pick this point. The B&E, though, of this quadratic rule can be or will be untruthful. So this opens the question or raises concerns about revenue and efficiency because truthful play may not be what bidders are actually going to do in practice. Right? And so the example, in a simple example called local, local, global, which I'll go into the details of in a second, we can see that the equilibrium of the quadratic rule is actually a rather significant shading of value. I should say in this plot, what I'm showing is the value of the bidder in this direction and their actual bid into the auction in this direction. So a shade is a drop in the line. And if, as an example, we're going to come up with new rules. This is one of them. I'll get more into details of them in a few minutes, but they're going to be represented by some other strategy space in this curve, and we're interested in figuring out what sorts of strategies are going to show up. So to be a little bit more specific, our research question here is which core selecting payment rule of these forms performs best in Bayes-Nash equilibrium in terms of the efficiency incentives and revenue of the implemented outcome. And to do this, we need to construct a framework for creating payment rules in this setting. And to do this, we generalize the fractional rule, which is sometimes called proportional rule, and parameterize it to cover all MRC rules. And to do this, you need to pick, or one needs to pick, a reference point, which we're going to denote R star, a weight vector W, and an amplification factor A. And then our rule is going to pick a payment P, which minimizes this term, which is a distance between the payment and the reference point that has been weighted by this weight vector and amplified by this exponential variable A. All of this subject to the payments being chosen being on that minimum revenue core set, or part of that minimum revenue core set. So this reduces the choice of picking a rule to finding an appropriate R star W and A. And to do that, we're going to pick a wide set. So there's been many proposed in literature. We're going to include many of those. We're also going to look at some new ones that are in this paper for the first time. And specifically, I'll highlight ones that have to do with Shapley values. So we're using a bunch of Shapley values to define reference points and weights. OK, so what are we going to do with that? Well, we're going to be looking with spectrum auctions in mind, very much along the lines of the previous talk. And we're going to expect in those settings for the players to be sophisticated, for the bidders to have a pretty good sense of their own valuation, and to be equipped with a pretty good idea of what other players' values are in distribution. That makes B&E a reasonable choice of solution concept. Real quick, what does that mean? It means that an expectation over the values of all other players, a given agent I will prefer its strategy over all possible other strategies. Okay, so how are we going to find these B&Es in practice? Well, we're going to need to look through 29 different domains. That's what I'll show you in a second how we constructed them, but we're going to come up with 29 different domains, and we're going to look at 366 rules, which are more or less the cross product of the things I showed you a couple slides ago. That's a lot of rules and a lot of domains. To find the B&E, we're going to use a computational B&E solver from previous work. The basic idea of how this works is that we're going to model the strategy piecewise with 200 adaptively placed control points, and then run an enhanced damped iterative best response algorithm to figure out how to move around those control points in order to produce a strategy. This is this very, very sophisticated animation that shows how this works. Let's see. Okay, so you can see it moves around the strategy to find the right strategy. The next thing we need to do is figure out how to evaluate the rules that we find, or in particular to understand the quality of the B&E that's obtained. For incentives, which is really the one that's most difficult to figure out how to look at, we're going to look at the average L2 distance between the true value and B&E, and it's really a probability weighted average. So that really boils down to the area between the strategy that we find and the true line. We're also going to look at revenue and efficiency, and then we're going to benchmark all of our results to quadratic, which is the rule that's used in practice. Okay, so some results. First thing to look at is the so-called LLG domain, which I promised to tell you a little bit more about. This is a domain with two items, A and B, and a local bidder 1 who wants item A, a local bidder 2 who wants item B. Both of these have values drawn uniform 0, 1, and a global bidder who wants both with value drawn uniform 0, 2. And as I showed you before, quadratic has an additive shade in this environment, and I should point out that it's already highly efficient in this setting. If we look among our 366 rules for the best rule by efficiency, we come up with this one. This is one that has a Shapley payment reference point, a VCG payoff weighting, and a very high amplification factor. And you can see that it gets a slightly higher efficiency. This is improvement over the number above, so it has a slightly higher efficiency. If we look for the one that has the best incentives, we get about a 5% lift, and it's now this blue line here. And the best by revenue is actually the first rule again. One thing to note here is that the rules that we're finding have this sort of large style. And what this means is that they tend to provide good incentives to bidders with large values. And you might imagine that this makes sense because large bidders tend to win a lot. So improving the incentives for them tends to help. Okay, so that was for the classic LLG domain. We've also looked at similar domains, but where we also look at correlation between the different players and also give the players a different marginal distribution besides uniform, in particular a whole set of different potential beta distributions that we've looked at. And we've also looked at varying the competitiveness of the local players relative to the global players. Here's an example from that kind of data. So this is a domain with cross correlation. That means that there's correlation between the local players. And it uses a beta distribution for the marginals, and in particular, this particular example has a very right-skewed distribution, so there are a lot of very large players in this domain. And you can see that quadratic in this domain has a very substantial shading, especially among the large players, and as a result, the efficiency is down to 95%. If we look for among our rules in this case, across all three dimensions, this rule is best. It's one with a bid reference point and uses Shapley payoffs for the weights. It gets about a 4% lift in efficiency, a very substantial improvement in incentives, and you should read this, the weighting here of the large number of rules on the right is why that does so well, right? Because there's a lot of probability mass over here, and also an improvement in revenue. So what I just showed you, though, was two examples for specific domains. We're also interested in what kind of rules would we find if we want rules that work across a wide swath of domains, rules that you might call all-rounders. They work in a lot of places. If you average the properties of the rules across all of our 29 domains and then sort and put the best rules top, you get a table that looks like this, and you can see that our top rules are performing very well. For most of these, there's at least a few domains where they don't quite beat quadratic. For the two rules that I've highlighted in green, it beats quadratic on all dimensions and all domains. One thing to note about what we see in this list is that the Shapley-based rules do very well. But it's worth pointing out that Shapley is hard to calculate in large domains, and so where I'm about to go, we're actually going to omit the Shapley rules because they're hard to compute in large domains. You can't tell from the slide, but these rules, these ones that are doing well, continue to be large-style rules. OK, so to see if these LLG-based results generalize to even bigger domains, we're going to look at the quad LGG domain, which is from this earlier work. This is a very substantial domain. It has 6 players, which are in these nice colors, and 8 goods, A through H. It's multi-minded, so this is a bid for the bundle AB, XOR a bid for the bundle BC. So it's quite complicated in comparison to LLG. Here I'm going to be looking at the version with standard uniform marginal distributions and no correlation to keep it simple. It's worth saying also that, as you can see from the picture, there's a lot of symmetries in this space, and that can be exploited to speed up the B&E search process. The actual strategy that defines how to play in this game is going to be a 2D surface for the global player and 2 2D surfaces for the local players, and I'll show you what that looks like in a slide or two. So if we take the top rules from LLG and then look and see how those rules behave in this larger domain, we find that they work really quite well. So the first thing I should say is quadratic is already 99.2% efficient in this domain, so there's not a lot of room above here, but still we can find some lift. We find quite a lot of lift in terms of incentives and some lift in terms of revenue. The other thing that we can do is we can look at rules that are very bad in LLG and see if they continue to be bad in the larger domain, and that in fact turns out to be the case. So this is a rule from way down the quality list on LLG, and it continues to do poorly here. We can also look at rules that are often used in literature, such as the proportional rule or first price, and you can see that they too also do poorly here. It can be instructive to look at the actual strategies that come out of rules like this. So the very top rule that I had on the previous slide is this one. That's plotted in these pictures in yellow. You can see that these planes are very flat and very close to the 45-degree line, which implies that they're very truthful. The quadratic rule is somewhat less truthful, and you can see that especially amongst the largest players where there's a pretty dramatic incentive to shade. These two are the 2 bundles of the local bidders, and there's quite a strong incentive to shade here and in there. For the global bidder, which is being plotted over here, there's actually, interestingly, a pretty strong incentive to overbid in this quadrant. So overall, I think you can visually see that the yellow rule is more truthful than the blue one. So let me with that conclude. The work here has designed core-selecting payment rules that outperform quadratic in all dimensions. At least a few of them will work better in terms of efficiency, incentive, and revenue. We've done this by employing an automated search through 366 different rules, including 6 reference points, 11 weights, and 6 different levels of amplification. We studied 29 different LLG-style domains and identified 20 really good all-rounder rules from within that set. And then we verified that the best among these continue to work really well in a much larger quad LGG domain, which is sort of the outer envelope of what our B&E solver can solve. Thanks.
Questions?
Yeah.
So I guess you could apply the revelation principle to any of these Bayes-Nash equilibria, and then as a result, probably the core property wouldn't hold anymore, right? Which I guess is fine if the purposes just to avoid complaints. Is that how you think about it, or?
Yeah, that's exactly right. Yeah, so there's lots of ways you can relax these or manipulate around them. Yeah, that's exactly what I would say. Yes.
Look at how it favors large or small bidders in any of these contexts, inequality among the payoff.
Yes, so there's substantial inequality going on here. We have a working paper that looks exactly at fairness and how to think about inequality among the different players. There does seem to be a pretty substantial trade-off between providing a fairness property and getting the absolute best in terms of the three metrics that I presented here. So in this paper, we're really targeting the three that we said, but if you had a different objective as a designer and wanted to target fairness, you would come up with a different set of rules.
So it cuts across and against all three of those metrics to go for fairness for the small guys?
It does in the sense that this push towards large drives the incentive property very strongly, and then that in turn drives the other properties pretty strongly. So it tends to be at odds with each other, unfortunately. Yeah. Yeah, they do seem to be that. Yeah. Cool.
Okay, let's thanks here again.